good afternoon, wherever you are. So we're very happy to have Professor Arun continuing to speak about Mcdonald polynomials, and today he'll talk about the connection with the asymmetric simple exclusion process. Yes, please. Arun.
Thank you. So first I want to, while I remember, because once I get going with mathematics, I will certainly forget to thank again the organizers for a wonderful meeting and all the participants that make it exciting. And especially thank you also for having me, because if nothing else, it forces me to work to try to learn some of this stuff myself. So that's good.
Yeah,
So
all credit goes to Venkatesh for organizing.
I'm grateful. Yes. So this talk in particular is really not the center of my world. I am usually just some sort of an observer from the distance of these topics, although I do enjoy it. So, for example, one of my very special friends is Percy Diaconis, and so we do talk probability often. And he certainly I don't really know any probability, but I know how Percy Diaconis likes to think, and so I think that way. But what happened to start this off was, so in particular for this ASEP thing, and I'm going to talk about the multi-species ASEP, maybe I'll write that. Multi-species ASEP on a circle. So this is a topic which, of course, Arvind is an expert, and I don't really follow the literature. So I hope you will correct me, because I don't know the history very well. And the way that I got started to think about it, well, there were several things, but one of them in particular was Lauren Williams sent me this paper. I was looking at my emails. She sent it to me on New Year's Day. So exactly 2 years ago, New Year's Day of 2019. And in it, they have this connection to Mcdonald polynomials. And I like to think I know a few things about Mcdonald polynomials, but I really didn't know anything about the probability side, except having heard some talks. And so part of my goal for this lecture and so on was to try to figure out some part of this story. So I will mostly follow the paper I just showed you of Courtil, Mandelstam, and Williams in the way that I present things. So lambda, I will fix lambda to be a partition, essentially, with capital N parts. And it's convenient for this story to make it so that the parts have size less than or equal to small n. So there are capital N parts, but small n. And I'm going to define now as a vector space, which is the span of some symbols. So bracket mu or ket mu is just a symbol. And there is one such symbol for every rearrangement of lambda. So this is the span of symbols that have, at this moment, they have no additional meaning, indexed by rearrangements of lambda. Okay, so now I need to fix a number, which is a probability. So it should be a real number between 0 and 1. And I'm going to define now the Markov matrix. So the Markov matrix for this is a transformation on this vector space. So it's really a matrix in my mind, but it's given in the following, by the following game. So you take your sequence, mu1, mu2, mu3, and you put them on a circle this way. So the last one. And you imagine that somehow these are some, I don't know, some people, mu1 up to mu n are their sizes. So, you know, there's one which is 100 pounds and another person who is 200 pounds, and you know, and they're in some rooms that happen to be circularly arranged. And every minute or so, one of the doors opens. So you choose random, so we can do it this way. We can make a little arrow like this. So this arrow spins around, you spin it, and it stops in some place, right? So you randomly choose, so choose a position in this circle by spinning the arrow. So this is uniformly. And then at that position, the door between the two adjacent rooms, it opens, right? And you see there's somebody in front of you and you in the room you have, and the door has opened. So if you are larger than the person in front of you, you know, if you weigh 200 kilos and the person in front of you weighs only 100 kilos, you say, forget it, I go first, and you put them in the back, all right? So then switch them. Because you're trying to get the sweets, you know, so you want to go forward as much as possible. So you kick the small guy back, and he has to go in the back room, and then the doors close again. And then you have to wait 1 minute, and maybe the door will open. The pointer has to go around and choose some door to open. And so if it happens the other way, that the door opens and the person in front of you is bigger. That's the problem, right? Because the person in front of you doesn't want to switch, because the person also wants to switch. And so you say, well, look, I'll make you a deal, you know? Let's just play a little game, you know? I have a coin here. We'll flip the coin, and if the coin comes up heads, then we switch, okay? Otherwise, you know, we leave it the way you are. So you flip a coin.
Is it a fair coin?
No, it's probability T. Of course, it's not a fair coin. Otherwise, you have no choice of convincing the big guy to switch with you, right? So it has to be, you know, probability 1/10 or something. So flip a coin. Probability of heads. Is T. And then if you get a heads, then you switch. All right, so this is the distribution, the way that we want to play the game. So this gives us a walk, and you run this walk for a long time, and you want to see, you know, what is the steady state of the system? You know, which big guys, do all the big guys go in front, or do, you know, what happens? Okay, so I made an example here. We can look at this thing. So you can see here that between these two guys, this
sorry, may I ask a question?
Yeah.
And what happens if they're equal?
If they're equal, then you just we don't. Because all we're keeping track of actually in the game is the sizes of the people, then you can imagine either they switch or they don't switch, or you don't really care.
Okay, thank you.
Because you can't tell the difference, because we're only keeping track of their sizes. All right. So,
Arun, I'm confused by the n. You're using n as lambda 1 through lambda sub n, and then there is a mu 1 through mu sub n. The subscripts are, I can't reconcile them.
Lambda, so the subscript, the number of parts of lambda is capital N.
Yeah.
And the mu's are just a rearrangement of the lambdas.
Okay. Mu's are, okay.
So in this example, capital N is 3. And I start with lambda, which is 2, 1, 0. And I put 2, 1, 0 on a circle here. But these are different rearrangements. And of course, there are 6 permutations of 0, 1, 2. So there are 6 possibilities for the position on this circle.
And if parts of lambda could be equal, right? That is allowed.
Parts of lambda could be equal. Yes.
Okay. Thank you.
It is allowed as a possibility, even though my example has all different. But here you can see that if I started in this state and then the door opened between these two, right? So then they could switch. But 1 is smaller than 2, so hopefully this this entry here is, I don't remember which way I did it. Did I do? So if 2, so that's, we start here, this is the big guy. The door opens between them. And then what's the probability that they switch? I guess it's T on N. It's either 1 on N or T on N, because the probability that that position got chosen is 1 on N. And then if you flip the coin, the probability that you get heads is T. So altogether, probability that you make that switch is T on N.
Sorry, that should be capital N, T by capital N.
T by?
In this case, it's 3.
T by capital N. Yes, thank you. Very good, thank you. Okay, and similarly, if the door opens between these two, and then they switch, so that switch happens with a probability also T on capital N. But this one, if the door opens between these two, so that there's a switch there, that happens only with probability 1 on N. I mean, because there's no flip of the coin. You'll definitely switch 1 on N to choose that position, and otherwise you definitely switch. So this is how you fill in this matrix. And I'm not sure if I did it actually correctly. I might have flipped the order around in this example, but you get the idea there. So the diagonal entry, which is here, you just compute this diagonal entry computed to make the sum of each column equal to 1. So each column describes a probability distribution which tells you the probability of going from a given state into the next possible states. Okay, so this is how what we get for this matrix, and it gives you a feel for what it looks like. Now, the first thing I want to notice is that, of course, I can write this matrix as a sum of smaller pieces, which I would like to call Ri plus 1 prime check. So I'm sorry for the notation, but there will be some connections later where this Ri plus 1 prime check is just a small 2 by 2 matrix, which is describing whether the mu I and the mu I plus 1 switch. Or they don't switch. And so that small matrix, of course, it has some diagonal entries, which I have to compute afterwards. But the other entries are just of this form, 1 and T. And if I put a 1 on capital N here, then I should have a true statement. Of course, it's interesting to notice that here already, when I write this, I have some periodicity built in. So these indices are taken mod capital N, right? And because I have also, I'm going on a circle, and so the possibility that the door opens between n and 1, so this could be a switch between the nth and the n plus first space, and the n plus first space should be the same as 1, the first space. Okay, so this phenomenon, indices taken modulo n, this is periodicity. And for me, periodicity means affine Lie algebra, affine Weil group, affine Hecke algebra. Something has to be affine because there's a periodicity here. Okay, so let me, that's the Markov matrix, and maybe I'll bring up so that we remind how we built this matrix. And so now the stationary distribution is an element pi in the state space with such that m pi is pi. So this is a good way to write it for my purposes. But the idea is that you run this system for a long time. And after a while, it should be somewhat stable. In other words, the probability of every given state, if you apply it, it doesn't change it. If you go, I mean, conceptually, maybe I should write it this way, is that m times m to the infinity of any state is equal to m to the infinity of this state. So you could just call this, i.e. m times pi is pi. So if m to the infinity, this is the way I think about it, is pi, then m times m to the infinity has to be m to the infinity. So the stationary state has to be an eigenvector for m, for the matrix M. I should write m lambda, sorry. Okay, so the stationary distribution is an eigenvector of eigenvalue 1. Okay, so now let me tell you the answer. To what is pi? In other words, compute pi for me. Well, in order to do that, I need to remind you again what we talked about on Monday about Mcdonald polynomials. So for, I'm going to let's let E lambda, so E lambda is a polynomial in now n variables, capital N variables, and Q and T is the non-symmetric Mcdonald polynomial. Which we talked about on the day before yesterday. So I won't redefine it. We don't really need to know any details about it, just to know that it exists. But we do need to remember that Ti is the operator from Daha that acts on polynomials. So the double affine Hecke algebra acts on polynomials, and we used this action to build the non-symmetric Mcdonald polynomials. Okay, so now let's let mu be some rearrangement of lambda, and let's let z mu be the permutation which I need to rearrange. So such that mu is equal to z mu applied to lambda. So I have some permutation which I need to rearrange lambda to mu. And let's let be minimal length. So that means that I could write T sub Z mu. This is an element of the Hopf algebra. Let me call it Tj1 up to Jk. If Z mu can be written as a product of simple transpositions, is a reduced word. Okay, so using this, then we define F mu to be the action of T sub Z mu on the non-symmetric Mcdonald polynomial. And I need to normalize it. Actually, maybe we should ignore all normalizations because I didn't really check them for this lecture. But this is called the permuted basement Mcdonald polynomial. All right, so it's really a polynomial F mu. It has in a bunch of variables x1 to n, and it also depends on q and t. So just to give you a feel for what it looks like, I have a list of the ones which would appear in this example. So these are the polynomials which would appear in the little small example that we showed before. But again, we don't really need to know any details about them for the moment, except to have a feel that they exist. There are some polynomials, they have variables x1 up to xn and q and t. Okay, so I will note that because we did talk day before yesterday, is that the symmetric Mcdonald, we did make this definition that the symmetric Mcdonald polynomial is P lambda, and it's just the sum of the F mu's over all the rearrangements of Sn lambda. So the symmetric Mcdonald polynomial is always obtained by symmetrizing a non-symmetric Mcdonald polynomial. So if you take an E lambda and you symmetrize it, you get a symmetric Mcdonald polynomial. Okay, so now I have set up the memory of what we had from before. So now I can write the theorem. And I actually, so maybe Arvind can help with the references. Let me write the theorem and then you can tell me what the correct reference is. So the stationary distribution which is, we had called it pi. So pi should be an element of my, well, I better give myself a bit more room here. It should be an element of my state space, right? So it's in I lambda. Remember that I lambda is the span of some symbols which are called ket mu. So I need some constants here, and these constants will be exactly F mu evaluated at 1, 1, 1, 1, 1 t. All right. And is summed over mu's. Okay, so the probability of being in state, so this is the probability of being in state mu after a long time, after minutes, right? So if you run it for a long time and then you ask, what's the probability that I'm in this configuration, this non-symmetric or this permuted basement Mcdonald polynomial evaluated at 1, 1, 1, 1, 1, 1 is supposed to be the answer.
Sorry, just to clarify, that's not, I mean, you have to normalize it. I mean, it's not necessarily less than 1. This F mu, you have to divide by partition function. Yeah.
That's probably, yes, that's right. Yes, so that's, and we do know explicitly what that partition function is, but let me just write 1 over constant. Yes, yes, of course. To make it a probability distribution. So at least from Cautil, Mandelstam, Williams, I understand that this is due to De Heer and Cantini, De Heer, Wheeler. Is that correct, Arvind?
No.
No.
This is, well, the combinatorial interpretation of the stationary distribution is due to James Martin at Oxford.
James Martin.
But this way of rewriting may be due to them, but certainly.
Okay.
Yeah, and also, yeah, these guys did have a role.
Okay. All right, good. So these guys, De Heer, I mean, we have a lot of people in our department here in Melbourne. De Heer, Wheeler are in our department here in Melbourne. Zin, Justin is also here. And Garbali is a postdoc, has been a postdoc or a research fellow, and probably Cantini also. You know, these are the people in your department who you say hello to in the hall, but you never talk mathematics, you know. But it's not completely true, because I do talk a bit mathematics, I try to. I also want to stress here that one of the people that I really did talk mathematics with was Foda. He really taught me a lot of what I'm going to tell in the rest of this. He passed away just a few months ago. For me, it was a great loss because he could translate from my language to the integrable systems language.
Oh, I didn't know he passed away, actually.
Yeah, he passed away in March or April, I think it was.
Oh,
yeah. So what I learned from them, some combination of them and the seminars around here, is the following theorem. Which says that let's actually just take the vector, which is given by the same kind of a sum. And again, I should normalize, but let me ignore the normalization. And let's put the actual permuted basement Mcdonald polynomial in there. Okay, without specializing. Okay, then this psi is an eigenvector for something which we can call Tn, x1 up to xn qt, which is an inhomogeneous transfer matrix with, and I think the right way to say it is Q-twisted boundary condition. Okay, so we were looking for an eigenvector for the Markov matrix, and that eigenvector for the Markov matrix turned out to be a specialization of given by specializations of permuted base Mcdonald polynomials. But if I don't specialize, I still get an eigenvector, but for a different operator. And the question is, what is this operator? So let me just give some sketch of how I was taught by my friends to think about this, this game. And that is that first thing is that this transfer matrix decomposes into blocks. And let's just call the blocks Tn lambda. All right, so first thing is that they decomposes into blocks like this. So the transfer matrix actually has all the Markov matrices for all the lambdas put together in one big thing. And the second thing is that since there is a product formula for this transfer, let me not write all the variables. So I'm going to write R01 of x1 over q, R02 of x2 over q, R0n of xn over q. So this I will explain a bit later. Where does this product come from? But then what this tells you is that you can expand this transfer matrix as some constant plus some term times, or let me write it in the other side. So let me take x1 on q minus 1 times some matrix plus 1, 2, and then x2 on q minus 1 times some matrix plus xn q minus 1 times some matrix plus higher degree terms. Okay, so we know, and this comes just because if you want to take, if you have a power series, if you have Taylor's theorem, and you want to take the coefficient of something minus the coefficient of the linear term, so I'm expanding in powers of xi, so I should write that, in xi on q minus 1. So I'm expanding in powers of this, and if I want to take the linear term, well, that linear term is going to be the derivative of your function at that value 1. So Taylor's theorem just tells you. And because this is a product, I can take the derivative using the product rule. And the linear term will exactly come out to be the sum of the derivatives of each of the factors. So this product formula is really powerful. And this relates us back to this observation that the Markov matrix is a sum of factors. So this part, so let me write on the next. So what we get from this is that Tn lambda is some constant matrix plus the Markov matrix, because the Markov matrix is a sum of these Ri, I plus 1, times, let me write it better. Let me write it better. So if I take Tn and I put all the variables to z, and let's put q to 1 and t, what I get is that there's some constant matrix plus z minus 1 times R12 prime plus R2, 3 prime plus Rn minus n plus 1 check prime plus higher degree terms in z minus 1, right?
Sorry, Arun, so there's a bit of confusion here because of notational issues. So m lambda, when you write as the sum of r prime, r check primes, it's actually a tensor product with identities on the left and the right, right? I mean, it's not, otherwise this would just be a 2 by 2 matrix. I mean,
yeah, but this is, yeah,
So-
you're right. But the same is true.
is that the same?
The same is true in this identity here. Yeah.
So,
Since I haven't defined the transfer matrix, it's hard to see this, but yeah,
so
you're right.
these R01 and R02 also have this tensored identities on the left and the right? Is it?
Yes, they have tensors in the middle between the 0, 2 and the 0. I mean, the indices are telling me which tensor factors I'm acting on.
Okay, so it's the same argument there, yeah. Okay.
Same argument, yeah. Okay, so this is the idea of how to relate these things. So everything is coming from this transfer matrix. So then I was bothering everybody, tell me, what is a transfer matrix? Tell me what, I don't understand. What is a transfer matrix? Tell me. But of course, you know, I live in Baxter land. So there are hundreds of people trying to tell me what a transfer matrix is, except that I can't understand any of them. Right? So this was my problem. So I went back to try to learn algebraic Bethe method. So this is following Takhtajan Fadeev, 1979, which is truly a wonderful paper. I really love this paper. So what do? So they start with the following setup. They say, let's let U be UTG, the quantum affine algebra. Well, they don't say it exactly that way because in those days there was no quantum affine algebra defined, but more or less that's what they mean. And then they say, let's fix two representations to be U levels integrable, level 0 modules, level 0 modules for U. So this is exactly the subject of what we talked about yesterday, was integrable level 0 modules for the quantum affine algebra. Okay, so what this means is that I have a representation of U as endomorphisms of V, and I have another representation of U as endomorphisms of A. And I'm sorry that I called this pi, because this pi has nothing to do with the stationary distribution. So but for me, I needed a representation. And I'm going to fix, or they will fix a positive integer. Okay, so then the physics starts. And the physics for me is always rather difficult. You know, my father was a physicist, and we fought about this this particular word, Hamiltonian, because at least for my father, life starts with a Hamiltonian, right? And I don't know how, you know, so I would ask him, what is a Hamiltonian? What is that? I never could get an answer, just something which is given by God, and it's in the beginning of existence, there's a Hamiltonian. So this is how they start. And after some work, you find that the Hamiltonian is a matrix which goes from V tensor n to V tensor n. And if you want to find this Hamiltonian, you are told that the Hamiltonian is the linear term of a transfer matrix. At least from the point of view of Takhtaj and Fadeev, this is this linear term plus higher degree. In Z minus 1. Okay, very fine. Since I'm here, I will go ahead and write down the partition function, because that's somehow, again, in physics, you're not allowed to not mention the partition function. So let's mention it. So the partition function is Zm cross n, and it depends on a parameter small z, and I think of small z as a value, and so it gives me a complex number, or you can think it as a function in z, which returns complex numbers. And this partition function is given in the following way: Zm cross n of small z is the trace on V tensor n of the transfer matrix of Z to mth power. All right. So what do you learn from this? Well, for me, I learned nothing, except that the transfer matrix is somehow also a good thing. It must be a good thing, right? So, okay. So then finally I ask, okay, tell me, I really want to know, what is this transfer matrix? Okay, so this transfer matrix, which depends on a parameter Z, so you should think of it as a matrix full of whose entries are all functions in Z, in the same way that this Markov matrix is a matrix whose entries are functions of T. This transfer matrix will be like that. And you look up and you find the definition of the transfer matrix, and that is that Tn of Z is the trace over an auxiliary space of the monodromy matrix. Right? I mean, for me, this was an infinite loop. It took me 20 years because, you know, I had to learn another thing, and then I would get tired and I would stop and I would go for chai, you know, and so I would never finish. And so it took me a long time to get there. It turns, so then this, but you have to be strong. So this monodromy matrix is a map from A tensor V tensor n to A tensor V tensor n. Okay, and what is its definition? Well, this monodromy matrix is pi tensor rho tensor applied to R of Z. Okay, maybe we can't go to put some of these notations on the other side here. Okay, so then I asked, well, what is R of Z? So there are two answers to that, depending on who you talk to. One is that there's an L matrix. So some people will say, well, it's the L matrix, and the L matrix is a matrix from A tensor V to A tensor V, and it's given by pi tensor rho applied to R of Z. Oh, so that's interesting. So that was interesting for me because, you know, if I'm a representation theorist, I cannot really tell the difference between some module and some module. I mean, V tensor n is a U module, and V is a U module, so the L matrix and the monodromy matrix are the same. Okay, that doesn't bother me too much. But what's really crucial is this R matrix. And so this R of Z is an element of U tensor U. And if I'm being careful, I should complete this tensor product, but let's not. And it's given by, so R of Z is tau of Z tensor the identity applied to R. You see, by this time, I'm just completely going crazy because this is just an infinite chain. And then it turns out that's the end. That's the initial data. So the initial data is U R tau Z. And this data is a pseudo quasi triangular Hopf algebra. So R here is called the universal R matrix. And it's part of the data of what it means to be a quasi-triangular Hopf algebra. So you get a U is a Hopf algebra, and this has this an additional element R, which is used to create a braiding on the category modules. And tau Z are some automorphisms of U. Indexed by Z in C. So Drinfeld wrote beautifully what are the properties of this initial data and why you want it to produce a good category. And so from this point of view, I can sort of go back to my youth because this is the same data that I need for Schur-Weil duality, for affine Schur-Weil duality, for SLN hat. Because, so U in this case will be UT SLN hat. And my favorite module of all is V is CN. That would be my favorite module for SLN. But of course, now I'm doing affine. So my favorite module is, I forget which, we use epsilon inverse, right? In fact, I have a picture of it here. Well, we can use, I think the pictures are also here. So it's a module. It has a basis like this. So it's a span of epsilon to the RV1 up to epsilon to the RVn with R and Z. And that's not very surprising if you, from yesterday's, when we looked at these modules, they all look like this. They have some finite basis, V1 up to Vn, and then they have this periodicity in them, which is this. And we can write down the action explicitly. We can even draw pictures of this module and what the action is of the quantum group on this. Okay, so now what does Hopf algebra mean? So Hopf algebra means we can take tensor products. Of modules. So I will keep the epsilon in this because So that means that I can look at V tensor n.
Sorry, and duals as well. Sorry.
And duals as well, if I include the antipode. Yeah. But right here at this moment, I only need the coproduct. So let's look at V tensor n. Well, V tensor n means that I'm going to take it spanned by tensors. I'm going to have to distinguish which factor this comes from. So R1 up to Rn here are integers, and I1 up to In are sequences, are elements from 1 to n. Right? So this tensor product has to look like this because I have to take the tensor product of vectors from my original space. But of course, I can rewrite this in this form, that this is the span of epsilon 1 to the R1 up to epsilon n to the Rn. And then I'll put the Vi1 up to Vin. But I could write that just as well in the form epsilon 1 R1 up to epsilon n Rn. And then V, there's no reason I should have called it I could have called it V mu1 up to V mu n, where mu1 up to mu n now is an element of 1 through n to the nth. And this is supposed to start to look familiar. From the very beginning here, we had sequences of length capital N taken from 1 through small n. Yeah. And so I might as well write this as the span of epsilon 1 to the R1, epsilon n to the Rn, ket mu. Or I could even equivalently write this as polynomials in epsilon 1 up to epsilon n, tensored with, well, I guess this is one way to say it. Or I could write this as a vector space as a direct sum over V lambdas, or even I lambdas at this point, I lambda of lambda decreasing. I can just group the mu's according to what they rearrange to. It's the same vector space. Okay, so that was a lot of action came from just the Hopf algebra structure. But now I have an R matrix. And an R matrix gives me a morphism, U module morphism, which we usually call R check, which will take V epsilon 1 tensor V epsilon 2 to V epsilon 2 tensor V epsilon 1. So the universal R matrix is exactly giving me such a morphism. And very often we write pictorially, we would write this as V epsilon 1 tensor V epsilon 2, V epsilon 2 tensor V epsilon 1, and we write the morphism as a crossing like this. Because the quantum Yang-Baxter equation, which is part of the data of the quasi-triangular Hopf algebra, will say these morphisms will satisfy the braid relations. So I get, well, let me add one more thing, and that is that the automorphisms, so the pseudo-quasi structure automorphisms give me a map which I would like to call Y from V epsilon to V epsilon, which is just takes epsilon to the R VI and sends it to epsilon to the R plus 1 VI. So it just multiplies on that component. Okay, so now if I take the following gadgets, so if I take Ri check to be the morphism which looks like this. So this is acting on V epsilon 1 tensor V epsilon n and V epsilon I V epsilon I plus 1 in the middle. And it's switching those ith and I plus first factors. And I consider, so maybe pictorially, I will draw this Y morphism this way. So then I can make a morphism Yi, which looks like on the ith factor, it just has a dot. So V epsilon I, V epsilon I. And on the other factors, it's the identity. So the Yix only on the ith factor by this special morphism. So these generate, so this is the very nice result, generate an action of the affine Hecke algebra on the epsilon tensor n, and this is commuting with the action of the quantum group of U. And that's the key word. That's the key word. Affine Hecke algebra. Because if you want to see Mcdonald polynomials, you have to see affine Hecke algebra. There's no other way to make a connection that I know of. And it is, in fact, exactly this appearance of the affine Hecke algebra, which seems to be the root of the connection between Mcdonald polynomials and transfer matrices for GLN.
Sorry, and here the Avaya is indeed commute as well, given the pictures commute, it seems, right? So
yes, they do. Of course, you have to check. There's a number of formulas to check in what I said, but yes, they do. So I'll stop there. That's, I think, enough. My time is up.
Okay, let's thank Arun for a very nice lecture. Are there any questions? Please feel free to unmute. Yeah.
Just one comment. I had the impression right at the beginning that those 2x2 matrices were generating were Hecke algebra generators.
Yes.
So in fact,
yeah.
You've sort of built in the Hecke algebra right from the very beginning.
Yes, but when you're looking at the probability, you don't always realize that, but you're right. So after we realize that and then make the Hecke algebra connect to the quantum group, then we're in great shape for, yeah.
So does this probability point of view help in studying things like multiplicities of Vermas, of simple modules in Vermas, or is it somehow completely tangent that you have a probability interpretation of all this Hecke algebra stuff?
Yeah, I'm probably not the right person to try to answer that question because I don't know probability to know. I mean, so but maybe Arvind, do you know if you can use the probability to get some multiplicity results?
Well, I don't know enough about the algebra side to comment. But there is a combinatorial interpretation, as I said, due to James Martin, and maybe that interconnects these two worlds. I mean, I would have to learn more about the algebra side.
Is the ASAP connected to Kasdan-Lustig polynomials? Have you ever seen that maybe?
No, not directly. No.
So is there an ASAP or some Markov chain for which the full Mcdonald polynomial itself will arise as a stationary distribution, I mean, not just the specialization?
Not just the non-symmetric one, you mean?
No. I mean, you specialized all the variables to one for the original system, right?
I understand the question now. I mean, it depends what you mean. So if when I talk to Percy Diaconis, at some point the stories become a bit too wide. But of course, you can construct lattice models which are colored and keep track of the colors as you go. And I think Borodin and his crowd, Borodin, Wheeler, and so on, I don't know, maybe even you, Arvind, are doing, I went to a few talks at a conference where there were a lot of talks about trying to do this kind of a thing where you keep track of the particles and their colors and how much they weigh and how big they are. And then you can get a lot more information and see some symmetric Mcdonald polynomials as partition functions and things like that.
But from what you said that the unspecialized version is an eigen function for some operators, right?
Yes.
That's the interpretation.
Yes.
So if I may add to what Arun said, some of us have been trying quite hard to get the Mcdonald polynomials out this way. But so the natural thing you might try is that in Arun's interpretation, the probability of choosing the door you can set to xi. Instead of choosing a door uniformly at random, you choose a door with probability xi. And this is the most natural thing to try, but that doesn't work. No. So one needs to do something more general, and we've been trying. There's some partial results, but nothing. But what Borodin et al. Do, this Mcdonald processes, is on Z. I mean, these are interlacing particle systems.
Yeah, but what about the Borodin-Wheeler? So there's a Borodin-Wheeler paper about, I forget what it's called now, where they construct the non-symmetric Mcdonald polynomials by using some very fused R matrices. And
okay. I don't know if that has a probabilistic interpretation. I mean, they might be using these constructions, but I'll check.
Yeah.
I haven't seen.
Yeah, it depends. So this is part of the problem. Is at what point does it become just algebra that you fiddled with, and what point is it actually probability? And I mean, the real answer to such a question is whether you can do asymptotics. But again, this is something that I'm too combinatorial to really do asymptotics in that way, because I work on very finite systems usually. But it is a big game, a wonderful game. It is good, yeah.
Any more questions? Well, if not, let's thank Arun again. I guess Venkatesh.
Arvind,